Good day, we are the team of Marco Antonio de la Peña Velázquez and Marco Antonio Alcázar Peredo, and we will be presenting to you the final project of thermodynamics. We will be talking about the first publication of Sadiq Cornet, which translates into reflections on the motive power of fire and on machines fitted to develop that power. Some concepts that are important to know before we start are the class statement that states that it is impossible to construct a device which operates on a cycle and produces no other effect than the transfer of heat from a cooler body to a hotter body. The Kelvin Planck statement that says that it is impossible to construct a device which operates on a cycle and produces no other effect than the transfer of heat from a single body in order to produce work. The motive power is an agent that does a work in a process that is most commonly is water, steam, or electricity.
The main purpose of this paper is to answer the question of whether the motive power of heat or the efficiency in steam engines is unbounded or it has unassignable limits, which nature will not allow to pass. So, it is worth mentioning that all substances on our planet are susceptible to changes in volume, pressure, temperature, and this leads to changes in the state of matter. Now, let's talk about the natural flow of heat. Carnot states that the heat goes from a hot body to a cold body. It cannot be the other way around because it will violate the second law of thermodynamics. And we can also say that according to Carnot, wherever there exists a difference in temperature, motive power can be produced. So go ahead, please. Okay, so now let's make a mental experiment. Carnot in his paper says that we should imagine two bodies. Body A with a hot temperature and body B with a cold one. We can assure that it's impossible to we put it in contact and then we can assure that it's impossible to return to body A the heat employed to raise the temperature of the liquid. But the inverse process, that is to give heat to body A, is permitted. This means that when we put these two bodies into contact, they will reach a thermal equilibrium, and we cannot return to body A the heat employed to raise the temperature of body B. So go ahead, please. Carnot also mentions two very important theorems. The first theorem is named about volume and pressure, that it's on the right side of the slide, and it says, when the gas passes without change of temperature from one definite volume and pressure to another volume to another pressure equally definite, the quantity of caloric or heat absorbed or relinquished is always the same, whatever may be the nature of the gas chosen as subject of the experiment. I'll give you an example so you can have it more clear. Imagine that you have 1 liter of air at temperature of 100 degrees Celsius, and a certain amount of heat must be supplied to it. Now we can assure that this quantity of heat will be exactly the same, that if instead of operating on air, we operate upon nitrogen, hydrogen, carbonic acid, gas, alcohol, neon, helium, argon, etc. On the other hand, we have the other theorem that it's called the theorem about heat and volume, that it says, when a gas varies in volume without change of temperature, the quantity of heat absorbed or liberated by this gas are in arithmetical progression, if the increment or decrements of the volume are found to be in geometrical progression. And I will give you an example to you so you can understand better. Imagine that you have 1 liter of air maintained at constant temperature and is compressed to half its size, let's say 1/2. A certain quantity of heat will be liberated, and this quantity of heat will remain constant if you go further in volume. If the volume of 1/2 reduced to a quarter, if a quarter reduces to an eighth, and so on. So go ahead, please. We are going to talk about, Carnot also talks about the conditions to create the most efficient engine. The first condition is that the temperature of the fluid must be as high as possible, so we can obtain a great flow of heat and in consequence a large production of motive power. A second option is that instead of heating the fluid, we must cool down the reservoir as far as we can, and we will obtain the same result. And the third proposition of Carnot is that it should be arranged that the passage of an elastic fluid from the highest to the lowest temperature should be to do an increment in volume. Okay, so go ahead. It can be said that high pressure machines are superior to those of low pressure, but this superiority not only lies on making immense pressures, but also it should be a machine capable of variable their pressures differing greatly from one another. So go ahead, please. Finally, I'm going to talk about the Carnot engine that Carnot presents in his paper. Let's imagine we have this cylindrical vessel. We have the initial piston that is in CV, and the piston goes to AB. So you go to the bottom and then again to CV, and you repeat this process again and again. Now imagine an external force came and make the engine stops at EF. Okay, so what's special about leaving this engine at EF? That if we now produce an increment, we go again to CV and EF, CV, CF, we will increase the density, the inelastic force, and the temperature in every cycle that you make. But the problem is that this is impossible because the steam would have required for its formation exactly the same amount of heat, but only the heat would have been employed at higher temperature. So the second law of thermodynamics tells us that this engine cannot be realized in reality.
Now we are going to be talking about the Carnot cycle. This cycle is divided into 4 steps. The first step is a reversible adiabatic process that turns the lower temperature into a higher temperature. The second step is an reversible isothermal process in which heat is absorbed from the reservoir. The third is an adiabatic process from high temperature to a low temperature, and the fourth is another isothermal process which releases the heat absorbed from before. The Carnot's theorem states that no heat engine operating between two given reservoirs can be more efficient than a Carnot engine operating between the same reservoirs. And here we are going to begin by stating that the reservoir from the Carnot engine is the new eta R, and the efficiency of the other engine, which is an irreversible, is the eta I. And so we will begin by saying that eta I is bigger than eta R, and then we will obtain that QH is bigger than Q prime H. So now if we want to obtain the net heat that is extracted from the low temperature, we obtain that it is the difference between these two, the difference between QH minus the work minus Q prime H minus the work, and we obtain that it is QH minus Q prime H. And so we can see that the net heat extracted from the low temperature reservoir is the same as the net value of the high temperature reservoir, meaning that in order to this to happen, there cannot be any work done. So we are left that this is false, and we are in this demonstration saying that eta R is bigger or equal to eta I. And from this theorem comes a corollary, which states that all Carnot engines operating between the same two reservoirs will have the same efficiency. So in this case, it is eta reversible 1 and eta reversible 2. So we will begin by saying that the second one is bigger or equal to the first one, but if we want to do it in the other way around, so in the reverse process, we will obtain that eta R2 is lower or equal than eta R1, and this is a contradiction, so we can end this corollary by saying that eta R1 is equal to eta R2. The Carnot efficiency, we can describe it as, we know that the temperature can be obtained by this formula, so the efficiency of Carnot will be defined as 1 minus QL divided by QH, but QL over QH is the same as TL over TH. So we obtain that the efficiency of Carnot is defined as 1 minus TL over TH. And in order for this to be the highest value, TL will have to be 0, which is called an absolute zero, which is something that cannot happen. And in conclusion, well, in the Carnot's paper, he talks about very important concepts that are relevant even now, such as cycle, reversibility in a system, the direction of flow of heat, the isothermic processes, the specific heats, and the most important of them all is the Carnot cycle.
At last, but not least, we can affirm that the Carnot cycle is the most effective cycle among all cycles, but it's only a theoretical one. So we can actually reach 100% of efficiency due to the second law of thermodynamics. So here are references, and thank you very much for your attention. Have a good day. Bye bye.